All right. Welcome, everybody. Thanks for coming. My name is Victor. I know it's that time in the afternoon when everybody's digesting food and doze off in their seats at conferences. Make sure you're properly caffeinated and ready to go. And I've been told that my voice is pretty mellow and smooth, and I'm just gonna try to make sure to not put you to sleep and show you interesting stuff. Come on. So today we're gonna talk about better tools in your Clang Toolbox, and it's a vignette in 3 parts. In the first part of the talk, we're gonna talk about tools exclusively. Mainly Clang Power Tools. And by the way, I have some stickers here on the table. If you'd like to decorate your laptop gear when you leave the room, please feel free to take as many as you'd like. The second part of the talk, we're going to focus on code, on your code base. Maybe you're working on a legacy code base, or even if you're working on a new project. And we're going to talk about massaging the code and code transformations and fixes that you need to apply to improve your code quality and be able to leverage the functionality that is empowered by Clang and LLVM tools in general. And the last part of the talk, that's the part that's the most important, and it's the call to action, so to speak, and the part where you get to actually take control of your code transformations and come up with custom checks and custom transformations specific to your code base, and make sure you stay in good shape and do a good code sanitization going forward and integrate these tools into your build pipeline and into your build flows and coding workflows. So let's start with tools. So I've been attending these kinds of conferences for years now, and I used to be very jealous and hanging around with fellow programmers, and they like to brag about the shiny new tools and their LLVM sanitizers and Clang checkers and tidy. And I've always been a little envious and jealous, and I wanted to get in on the action. But I've traditionally always worked in a Windows environment. I've always developed applications targeting Windows, although in C++, and I've always been in Visual Studio almost exclusively, or since very old versions, up until the latest version of Visual Studio. And I'm going to continue to work in this environment, and we're going to continue investing in using this workflow and working with these tools. But I wanted to leverage all the goodness and all the facilities and all the innovation in the LLVM ecosystem on Windows, in our own IDE, in Visual Studio, on our own terms, on our legacy project. And I've been working on a project that's fairly big now. It's a fairly big code base, a little over 3 million lines of C++ code, developed over 15 years now. And although I've been with the project almost since its inception, there are still lots of words and parts of the project that we're not so proud of, and we're striving to improve them and modernize them and find out if there are any bugs or latent problems in those not so well tested parts. So Clang Power Tools comes into play and basically brings all the goodness and all the shiny LLVM tools in our friendly and our favorite Visual Studio, our friendly C++ IDE. So it's a free open source Visual Studio extension. We have a website, and it's a plugin. You can install it right away, and you can leverage the LLVM tooling right in your favorite IDE. So as I said, we've used it to perform various code transformations and modernize our code base to modern C++ and find bugs that were surprising, and we're going to continue to use it and keep it integrated in our workflow. And we think we found a good way to balance being extra thorough and running it regularly, and still being productive and being able to go about developing in our day-to-day LMS cycle. So the project is a little over a year old. We launched in September 2017 at cppcon, when we announced the first version of this tool. And it's quite, it took us by surprise, the amount of enthusiasm in the Visual C++ community around this tooling, and how many developers have embraced it early on, even when it was not so great. And we've had lots of bug reports and feature requests and even pull requests from the community, and people were very enthusiastic in getting early on the action and using it and integrating it in their build environment and finding problems in their code bases and leveraging the Clang-tidy modernizers with it. So it had an unexpected success, and we've learned a lot because of this, because we've interacted with many outside developers, and we've seen lots of different scenarios and ways in which it was used. And we've learned a lot about Visual Studio, the Visual Studio build systems, and Visual Studio property sheets, and MS Build. And we've discovered that people out there in the community, they are using build scripts and Visual Studio project files in ways in which we haven't imagined before we started open sourcing this tool. And interacting with the community has been very eye-opening for us, and we actually learned a lot, and we applied some of the learnings within our build workflows as we fixed and added features to these scripts and tools. So I have to give a shout out to my friends Gabriel and Ionuț, and they are the brains behind the projects. I get to speak for this project, but they're actually doing all the heavy lifting. And of course, the community contributors that came with great feedback and even patches to the project. At least, if you don't have the time to spend to contribute to the open source effort, at least if you're using it, please do report bugs that you find. We try to be very agile in fixing them. We release almost every 2 weeks or 3 weeks now, and we try to triage and investigate and fix issues as soon as possible and prioritize them, of course. So at least submit bug reports or enhancements or suggestions that you might have, and we'll try to address them and prioritize them. So do check it out on that GitHub link there, or just Google it. So it started not as a Visual Studio extension, but it started rather as a PowerShell script, because we initially wanted to consume it internally and leverage this functionality in our build environment. And we started scripting it, and later on developed it as a plugin for Visual Studio for the developer workflow. So the PowerShell script, that it's still at the core of the extension. The extension itself uses these PowerShell scripts underneath. It's very configurable, supports both the compilation and tidy workflows, works directly on Visual Studio project files, so there's no need for round-tripping settings, no need for defining a JSON Clang compilation database. The scripts automatically parse the projects and your solution files and discover and translate all the Visual Studio specific settings into something that Clang can consume. Supports parallel compilation, which is a big deal if you're working on a big project like ours, and constructs Clang precompiled headers. In the Clang community, PCH is not such a big deal, but on Windows, it really saves up a lot of build time. So we leverage it a lot in Visual Studio projects. So we actually build a Clang PCH for every project and a PCH configuration file that we may have in Visual Studio. And of course, automatically extracts all the necessary settings from Visual Studio projects, like compilation settings, the definitions, include directories, and everything that's needed to compile your project. So this is where the tricky part is in this footnote. Some example of configurable knobs for this script. and very useful for continuous integration and CI pipelines. And we actually use this script in our build servers to make sure that every commit actually passes certain criteria, certain verifications and checks that we need to impose. So you can use it directly with all those switches and have low-level control over the configuration, or a newer thing that you can do in Clang Power Tools is actually leverage a config file that you can actually place in source control. And this is the route that we've taken, because the complexity immediately got out of control, and too many configuration settings needed to be set. And you can actually specify a config file, and basically every command line option can be translated in an XML config file that you can store in source control and share with your development team. Some example usage, basically direct invocation in current directory and automatically scans for Visual Studio Solutions and project files. You can be explicit about ignoring some projects that you don't need to compile under Clang or check under Clang. You can be specific about ignoring certain source files that you know, for example, they might be a third-party library or third-party source code that you don't have any leverage on, or you cannot modify, and it's not Clang compliant, or it's not ISO C++ code. So you can be explicit about ignoring projects or files, and you can be explicit about which tidy checks you get to enable, like this example here, where we disable all the default enabled checks. That dash star there means disable all the default enabled checks. Tidy has a list of enabled checks by default, and just run the modernized checks, every modernized checks that matches. I think it's easier to follow in a config file. For example, the config file specifies Clang compilation flags. We use the GCC driver for Clang, so we take in switches and all the parameters that Clang++ expects. So if you're familiar with Clang++, these will be very familiar to you. So we started with an ambitious set. It was not exactly like this, but very close. For example, treating all warnings as errors. We were not able to start with WAll right from the start. There were too many warnings, so we had to gradually adopt and fix the issues and gradually strengthen the warning levels enabled. And I'm going to talk about this a bit later, about gradual adoption, because it won't be as easy as flipping a switch and you're off and going. And you can see here file ignores, project ignores, and everything I talked about earlier. So this can be easily edited and versioned in the source control. So for CI and your build servers, we use Jenkins right now. We're in the process of switching to GitLab Runner, but we've been using Jenkins for over a year now on this workflow. And independent of which build CI/CD automation system you might be using, the configuration steps are basically the same. But I'm going to use Jenkins as an example. A very quick overview. You need to install, if it's not already available, the PowerShell runner. So some sort in Jenkins it's a built-in plugin that's able to run PowerShell scripts or something similar to that, to be able to run shell scripts. There you go. You can add a build step in your build pipeline, to run a shell script, and you can invoke the PowerShell script with the required switches, or if you do not provide any switches and you do have in your working directory for this job or this pipeline, if you do have a Clang configuration file, it will be automatically discovered and the settings will be automatically applied. You can configure it, for example, to pull source control for changes and trigger verification and builds for each new commit that comes into your branch, your target branch. For example, you can configure it to automatically monitor the master branch or the develop branch, either whatever Git workflow you're using. And whenever a new commit is merged, you can automatically apply like a linting step that's a lightweight build that you can do to verify that it meets certain requirements. And you can use, for example, nightly builds if the project is bigger, to do verifications that are more expensive or time-consuming, like various analyzers in Clang-tidy. Those are not immediate for larger projects. We have notifications configured. For example, we use internally Slack for communication, and we have a Slack bot that automatically pings us when a build is broken. For each pipeline, you can configure such a thing in your build server. You can trigger email notifications for build failures with detailed failed builds or failed checkers that do not meet the validation required in that pipeline. For example, an analyzer step or a build failure under Clang. Of course, this is not suitable for analyzers. Analyzers are the kind of things that you want to integrate in your development workflow and run on a regular basis, but it's not something that you need to integrate in your CI/CD pipeline. That's not suited for that. For the developer workflow, of course, you want all these things accessible from the Visual Studio IDE. So we like the Visual Studio IDE. We think it's the best development environment for C++ on Windows. And we like the Visual Studio debugger, and we like the Visual Studio built-in CPP core guidelines checker and analyzer. And you cannot have too many analyzers or too many checkers, because they report different things and they have different levels of noise versus useful information. And it's always good, for example, when dealing with checks and doing static analysis, it's always good to have multiple sources to identify and pinpoint various kinds of informations, and have different ways of displaying diagnostics and mining that information. Because with lots of diagnostic information, that it usually comes with high noise ratio, and you want to have multiple sources to intersect that information. So you can find the extension in the Visual Studio Marketplace. Install it right from within Visual Studio. In terms of configuration, every knob and switch that can be configured via the Clang configuration file or via command line for the PowerShell script has a friendly user interface in Visual Studio that you can toggle everything from and customize it and persist it per user settings and migrate it across your machines and everything. So, for example, here, a useful compilation scenario that we use is, for example, Clang compile after MSVC compile. For example, when you're compiling a CPP file and it passes compilation successfully under Visual Studio, you can automatically run a background compilation under Clang to see if it also compiles under Clang. We found that this scenario ensures that we don't have any build breaks in our CI pipeline. For example, developer compiles everything in Visual Studio, pushes commits, and later on, Clang build is broken on the build server. Later on, it's very frustrating coming back and amending commits and pushing fixes just for making sure the code is compliant and the build succeeds under Clang. So this workflow really helped us. Here is where you can configure all the warning levels and be very specific about ignoring certain warnings or not, being selective in ways in which you choose to ignore specific warnings, be it at code level or project level, and ease your way into adoption of using LLVM tooling on Windows. Because, as I said, it won't be straightforward. You won't be able to go W all or W extra right from the bat. Unless you're starting a new project, of course. All my experience comes from dealing with these kinds of tools in the context of a big legacy application that we're trying to work on and keep releasing on a monthly basis and modernizing it at the same time as we develop features and find and fix bugs in it. So, for example, custom checks, you can run predefined Clang-tidy checks. You can define them by name. There's a built-in list with all the predefined checks in Clang-tidy. There's built-in documentation for each check, so you don't have to go to the web and read about it. You'll find it in this snippet section, the short documentation for that check, of course, not the long form. You can also wildcard match checks and build, for example, run all the modernized checks or all the readability checks, not every check. It's unfeasible that you will run all checks every time, because you generally want to focus on a particular type of check and see all the instances or all the incidents reported throughout the project, rather than being all over the place and checking for everything at the same time. So most likely you'll focus on a particular check, and once you're done with that, you're going to move on to the next one, and the next one, and the next one. Some checks are related to each other, so it's okay to check them at the same time. So you can save a bit of time going through the code base like this, because you're basically combing through the code base and investigating reports. But most of them you have to apply them methodically in terms of static analysis. And you can also specify custom checks, of course. The usual places that you would expect integration with the IDE, of course, you can run Clang compilation or Clang-tidy at project level, at solution level. You can run on a current context, on the current selected tab or file, source file. There's a toolbar for easy access. There are keyboard shortcuts, everything you would expect from a proper IDE integration. You can run on particular set of files that you have selected in your Solution Explorer. You see the compilation error right within the IDE in the output pane. There's a dedicated output pane for Clang Power Tools. I don't know if you can read this. There's a dedicated pane, different from the regular output from Visual Studio, but in the familiar location that you would expect, of course, with code navigation and click to go to navigate to the proper line and everything you would expect in an IDE. Same for Clang-tidy analyzer report. You see the built-in report with the from the analyzer, and you can navigate to the error and deal with it in the context of your project. So there's no separate off-the-side reporting. And we do have plans to integrate right in the editor window with helpful tooltips and fixits right in the editor window itself rather than the output pane. But that's in work in progress right now. So why do I care about this? As I said, I'm working on a fairly old project, pretty big. We're not such a large development team, but we've managed to Clang-tidy our whole code base, and we've managed to build it over the course of a summer with a few brave lads that joined the effort in my team. So we've been able to make it ISO C++ conformant. We've been able to modernize large parts of the applications automatically, leveraging Clang-tidy modernizers. And we've integrated in our workflow, and we're keeping it running as we go along now. So this is core functionality for us. It's part of our workflow now. We couldn't imagine running and building the project I work on without actually passing all these conformance steps and analyzer steps. It used to be something that it was like a chore, something like that was difficult. Now it's part of our workflow. So it's something we do regularly. So just to gauge the audience, how many of you, I know some of you might target different compilers based on your different projects within your teams, or maybe you're targeting various operating systems or operating system versions, and I'm interested in the lowest denominator option. So if you're targeting something like C++ 14 and C++ 11, I'm interested in the lowest target that you have. How many of you are still stuck with an old C++ version, like 9803? Oh, I'm so sorry. How about 11? Okay, about half, I would say. 14, even fewer. I'm scared now. 17? About a third, I would say, just for the camera. Okay, so that is where we're trying to go. So we're trying to rejuvenate an aging project, or maybe we're trying to, if we're working on a newer project, we're trying to see if we're using the best tool for the job, if we're using the most modern and most efficient components, most modern or efficient facilities from the library or the language, and this is why we need to go that route. It's not like an intellectual exercise, it's something that has immediate benefits. Also, in the process, what we've learned on doing this ourselves is that we've uncovered a ton of bugs and issues while trying to fix compilation and get rid of Clang warnings. So warnings are there for a reason. So of course you're striving for C++ standard conformance. Maybe you're not doing cross-compiler work or cross-platform work, but staying conformant really helps you be a good citizen and not make huge mistakes by leveraging non-standard language extensions. Because if the compiler allows them, and traditionally they've been there for years, people are going to leverage them and bad things usually happen. So it's all about finding bugs. Who here has heard about MSVC permissive minus? Permissive minus. A few people. Okay, so for the other people in the room and the ones watching, permissive minus is basically turning on a different compiler in MSVC. MSVC actually ships two compilers. The old, like 30-year-old C++ compiler, that's a YAC-based compiler that has some modern C++ features, as most as it can be implemented on a compiler that doesn't have a full AST, and a modern compiler that is full AST compiler, recursive descent compiler that's a modern and implements all the modern features up to C++ 17 and even C++ 20 features. I'm talking about language features, of course. And whether you specify this switch or not is whether you get access to the new compiler or not. For new projects, this is on by default now. For older projects, of course, it's off because you need to preserve compatibility, obviously. So this is what you want to strive for if you want to access the newest and the most complicated features, like if const expert, for example, with full grammar, and if you want to access all the modern features of the language, this is the compiler you need to strive for. And this is what you need to have enabled for your project going forward. But there is a problem. It's not straightforward. You cannot flip this switch and automatically work, because if it did, they wouldn't ship to compilers. So the problem is older Windows SDKs. So they had problems themselves in the Windows SDK that used non-standard constructs and did leverage some language extensions there, and they fixed them in all the modern versions of the Windows SDK. But older SDKs are a problem because they will not compile under permissive minus. So why would you bother with older Windows SDKs? Well, for example, if you're targeting Windows 7, or some of you are still targeting maybe Windows XP, like we do. So there might be reasons why you cannot be on the latest and greatest Windows SDK. So I'm going to give you some pointers in how to deal with that. But the latest Visual Studio STL actually is in very good shape. One thing that you need to know is that using Clang and LLVM on Windows, there's a pre-built binary that you can download off llvm.org. So it's an installation kit that you double-click and it installs everything. It's very straightforward. But it doesn't ship with its own STL. So it actually uses the STL from MSVC. And luckily, the people working on the STL from Visual Studio actually makes sure that it compiles properly under Clang. Under, of course, latest version requires Clang 7, so it no longer works with Clang 6, but older versions used to work with Clang 6. So they make sure that the STL implementation on Windows actually compiles on Clang as well as MSVC, under permissive minus as well, of course. So the STL is in pretty good shape. The only problem are the old Windows SDKs there. So the goals is, as we set out, again, more like a case study for us. We started with Clang format, easy, something that we needed to make sure that we don't have any more curls in code reviews. About white space, building on the success of Clang format adoption, we gained courage and we experimented with Clang-tidy and Clang compilation. And the problem was getting all the code to compile under Clang. That was the big hurdle to start with. So maybe this is a possible route for you as well, but who knows? So we have found several compatibility issues between the two compilers, and I have a few examples. And just as a note, we were already on the highest warning level in MSVC, warning level 4, and we had no warnings in the project. We used WX. That's treat warnings as errors. So, but there are non-standard C++ extensions, and the MSVC compiler happily accepted those, and people use them. So we fixed all of those, and we performed refactorings, like I said, and static analysis, and we finally managed to switch to permissive minus. That took a while, but we got there. Just a few examples. For example, delete was called on a class that had virtual functions, but not a virtual destructor. Those can be bugs, and we found situations where it wasn't a harmless warning. It actually was a bug. Overloaded virtual functions. We had functions that actually added an extra parameter and automatically masked the virtual function that was inherited. Loop analysis warnings, for example, iterators or loop induction variables that were incremented twice, once in the for loop declaration and once in the body. Accidents like that might happen. People that try to be clever and try to do moves. When people discover move semantics, all they see is move opportunities. So people that try to be overly enthusiastic and applied move operations where actually is a pessimization because it inhibits copy elision and forces a move. And sometimes a move is can be an expensive operation in itself. So copy elision is better. Doing nothing is better than doing a move. And we found a handful of situations like this. Lots of instances where the member declaration within the class didn't match the initialization order in the class init list. You know those, I'm sure. So we actually had to build tooling to reorder these and make sure that the order was consistent, because in some situations we found that there were dependencies between the initialization order, and there were situations where there were pointers that were improperly initialized, and so we basically had undefined behavior there. Missing field initializers in structs and aggregates, we had lots of those as well, so we had to manually fix a lot of those. A frequent offender again, double user-defined conversions. For example, here we're trying to get to a locale facet from an array of wide characters, and we have to pass through a double conversion, first through a standard string and then to get to a conversion constructor in the facet class. So we had lots of those, and Visual Studio happily accepts these double conversions that are disallowed by the standard. Under permissive minus, this will no longer fly, but under the old MSVC compiler, you will have lots of this. Again, delete with no virtual destructor. A common pattern around using smart pointers. Smart pointers having interfaces within them, and when they try to dispose of the underlying heap object, the actual destructor was not marked as virtual. So we had quite a few instances of those, so that's a generous memory leak there. Again, other situations with interfaces or abstract classes around custom deleters and unique pointers, same thing. We found quite a few instances of memory leaks around destructors that were not marked as virtual. One that was pretty funny, it surprised us, because we found quite a few instances of this, and some of them were harmless because they accidentally matched in numerical value. For example, being an older code base, we didn't use enum class, we used traditional enums, and you can easily mix up enum values that had the same spelling but were actually different from different enums. And sometimes then matched in numerical value, and there was actually no bug, but we have actually found instances where regular was not the same value that it's supposed to be because it was from a different enum, and they were both in the same visibility scope. So Clang actually checks this, and we caught quite a few of these. Some of them were harmless, but either way, risky business. On iterative conformance, some advice I can give you from what we've tried is doing it gradually. For example, enabling only a certain class of warnings or suppressing certain warnings explicitly, like I have a few examples here. So Clang happily has various knobs that you can leverage to either mute some warnings or enable a class of warnings or toggle some compatibility on Windows with the MSVC compiler. There are some compatibility switches with MSVC that the Clang driver uses. So there is a path there, but you need to massage configuration settings a bit and see what works for you. The long road to MSVC permissive minus, I'm happy to say that we're there, but it took us a little while. Two kinds of problems: issues in your code, of course, and dealing with older SDKs, like I said, for targeting older Windows operating systems. For issues in your code, usually there are lots of issues related to template two-phase lookup, and the most simple fix in most of the cases here was actually including the required headers for everything that you had implemented inline in your template classes. They need to be visible inline in that header file, not later at the usage site. So the most easy fix that was applied for lots of these was actually included the required code. Fixing issues on related to dependent types for templates, again, you need to be more explicit and more verbose here, but it's quite a mechanical fix, but you need to pay attention. And do not assume the STL headers include each other, because as the library evolves, things change. So you need to be explicit about including each functionality that you need. A thing that came up frequently for us was S-stream, I think, or some kind of locale header that people didn't include explicitly, and they assumed it was included because in the past it was included by another STL header. So make sure you're explicit about your STL dependencies and include all the documented required headers. For dealing with the SDKs, a frequent offender, if you're targeting, for example, Windows XP or Windows 7, hello COM, if you're using COM, or including some header that has ties in Windows COM, you do need, because of the template machinery, you do need to forward declare struct enum before including those headers to get rid of that warning. Again, it's related to two-phase lookup in templates. And this is a frequent one. Again, if you're dealing with older Windows SDKs. Strict strings is a machinery that is off by default in the MSVC compiler, but if you switch on the new compiler, or if you're using a newer project, that has permissive minus. Permissive minus implicitly sets the strict strings policy, and that basically checks that you have proper const qualification for string literals conversion to actually pointers to characters. So this was very frequent offender and a source of situations where you're basically in an undefined scenario. But if you need to deal with this kind of situation, what we did was actually disable strict strings in the permissive minus scenario for those specific SDK headers. So if those headers happen to be in your PCH file, then you need to disable strict strings for your PCH files. If the situation is more localized, then it's a happier case. Then you can disable strict strings for that specific translation unit or compilation unit. So luckily, the Visual Studio compiler in the project allows you to specify these switches at source file level. So if you need to go down to source file level, you can actually disable this warning at a specific offending file. So I always include links and references in my slides, and if you get a chance and get the slides after, you can always check out the references that I have in the slides for each mention that I have. So after all this effort, we were also able to get rid of all the Microsoft compatibility flags in Clang. So we no longer need those. And basically, as long as you're on permissive minus, MSVC and Clang are in agreement with what's conformant and good quality C++ code. So you don't need to make special cases or special tricks to silence or make happy any of the two compilers. So basically, they're on par on what constitutes ISO C++ conformant code. So no more compat code. So yay. Okay, about tidy. Clang-tidy has lots of built-in checks. I think there are almost 300 now. Large-scale refactorings we performed. Some of these I listed here. I won't go into details in all of them. We basically analyzed and saw which of the built-in checks were useful for us and which yielded results that we can actually apply. So, but there were problems. For example, like eliminating redundant sister from a standard string. There are lots of instances where this was dangerous because we actually treated that string like as a buffer, as a non-terminated buffer, and we needed to construct it as a string. So these, you better watch out for this. Again, watch out for automatic replacement of news with make uniques. You need to make sure that you have the proper specialization of make unique there that has byte bracket bracket. Again, lots of, after using modernize, use auto. This is a very nice transformation that we applied, and we replaced all these ugly type defs with iterators with auto, but you're left with a bunch of junk type defs that are no longer needed, so you need to get rid of those because they're basically unneeded type definitions that clutter your code after using auto. Again, we've modernized a lot of for loops that used iterators, and we were left with a bunch of unused orphan values like sentinel ranges like first, last, or count that were no longer needed, and we needed to clean up all those orphan values. Luckily, these were pointed out by the compiler itself after the modernization. Ironically, it doesn't do it itself, but at least you can catch them and get rid of them immediately. Function pointer declarations, that was the most horrible thing that we encountered. Surprising results around calling conventions and pointer to functions that used macros to define calling conventions on Windows. I wouldn't recommend doing that. It was very time consuming and didn't yield good results. again, using around some replacing type name with using for some template type declarations. In some instances, it didn't yield proper results in terms of actually replacing the template type with the last concrete type of the, the instance that it encountered. So luckily, these are not silent issues. You usually catch them in the compilation step afterwards. So, but they, in some situations, they messed up the code. So you better watch out in the diffs. Don't assume the Clang-tidy modernizers just work amazingly, and always double check and make sure they do the right thing, and inspect each line of diff. Beyond Clang-tidy, how are we on time? Okay. Beyond Clang-tidy, we wrote custom tools for our specific needs in our project to look for specific constructs in our code. I mentioned the member init initializer order, the unused private fields, and we refactored some heavily used constructors within our project that needed some attention. An interesting warning: unused private field actually removes class private fields like references, pointers, and regular pods from the class that are private and are not needed. It warns you about it, and you can remove those. But you have to watch out for orphan method declarations in classes, because if you have a private field that is unused, but you do have a private declaration of a function in your class, even the compiler it's not a linker, so it doesn't look up, and it assumes that you have a definition for that function somewhere. So only the linker would complain that you wouldn't have a definition for that function. But if you're not calling that function, so if it's really left over, and we had some instances of these functions that are declared but never called, the linker is happily to ignore that, and Clang cannot assume that you're not using those private fields, because you have private fields, but you have functions that the compiler doesn't see the body for, and it assumes they're in a different translation unit and doesn't warn you about them. So we actually had to build separate tooling to detect these orphan method declarations to make sure that we remove those and then uncover more private fields that were left unused. So cleanup is hard. Deleting code is harder than it seems. On the roadmap, we're working towards W extra. Right now we're on W all, but we're working on W extra, and we're working on improving the extension and the analyzers, and running them and fixing issues and adding more code-specific transformations, of course. And about taking control, more Clang-tidy checks. This is the part where I'm trying to give you a feel for what it takes to build a tidy check. Checks can plug in the analysis at a preprocess level using PP callbacks, or on a AST level in Clang using AST matchers. Usually, most checks that you would need to write are at AST matcher level. So checkers can report issues in a similar way that Clang Diagnostic does, with a message or a fix-it that can be automatically applied if the user wants that. And there are some tools to get you started in the LLVM extra repository. There's a Python script to add a new check that automatically creates the check, updates the CMake file, and creates test unit and file templates for you to fill in with with your code. You can use Clang Query. It's a tool that you can use to interactively prototype AST matchers and explore the AST for your program. You can use Clang Check to dump the AST and examine the declaration, so you can identify what exactly are you trying to match in the structure of your program to make sure that you properly discover its structure and the types that you need to deal with, because you're not Clang developers, so you don't know those type definitions by heart, so you need to discover as you go. So a sample structure for Clang-tidy check in terms of source files would be something like this. Basically, it's fairly easy to get up and going. You just clone that repo and the extra tools repo, and you just execute the build file and make check Clang tools. It's fairly straightforward. And then you just run the Python script. For example, here I'm creating a new pretty func check in the readability module. Tidy checks are organized in modules. So basically this will generate for me a pretty func check header and source file, and it will enable it in the readability module by creating a readability tidy module entry for this new check. Its structure is something like this. That's the most basic structure that you can define. You have to inherit from a Clang-tidy check. That's a base class for all the checkers. And you have two functions: register matchers for AST matcher and check that actually does the check. As I said, for preprocessor checkers, you have to use pp callback. And registered matchers registers a Clang AST matcher to filter out the interesting declarations. So this is where you define what you're interested in your particular check. What pattern are you looking for? A method declaration, or a definition, or a particular construct, or an expression that you're targeting in the structure of your AST. And the check function that actually is called when Clang detects that pattern that you declared. And this is where you can take action. As I said, if you're working on a preprocessor level, there's a different register method. So, for example, here, I'm adding a matcher for a function declaration. And this is all I'm interested in, function declarations. And I'm giving it an identifier, so I can later in the check function make sure this is the one I define, because you can define multiple matchers. So you might be interested in different kinds of things and then deal with them independently in the check function. So that needle is just an ID that I give this matching predicate. So basically I'm binding this predicate to an ID. So later on in the check function, I make sure I get the right matching declaration that I was interested in. And a very basic check here, I make sure that the function declaration starts with get underscore, and I'm trying to get it to replace it to get with uppercase with no underscore, because that's how I like them. Of course, it issues a diagnostic message like you're used to with Clang-tidy checks and the Clang compiler, and it offers you an optional fix-it hint, so we can actually replace and tell you that hey, you can replace this with that. So this is the most simple and basic check that you can write, and as you can see, it fits on the slide. It's the code, the whole code fits on the slide. Not all checks are going to be this simple, but for explanation purposes, it serves the job. But I do see a problem here. Do you see it? No? It's because we're here. So we're in east const. So there, I fixed it. Now it's east const. And yeah, like they say in UK, say it, sort it. So that's my policy on east const. So if you want to test your check, you just run it regularly, like you run any other check, by disabling all the built-in checks that are enabled by default, and enabling just your check that we named our check pretty func in the readability modules. So it's readability dash name of my check, and working on the test file that is file cpp there. So straightforward like any other built-in check. If your check needs configuration options, Clang-tidy provides hooks for checks that can be leveraged, and you can enable even the built-in checks. Some of them have levels of customization. For example, for loop analysis, you can customize how aggressive it can be. It has some policies in terms of how aggressive it can be in replacing or analyzing what can be done. And you can define default values. For example, for our check, we can define which pattern to look up. By default, it looks up get underscore. But you can let the user that runs that check get control over what the check does. and many checks do this, and it's very easy to get forward as a basic property syntax that you can define properties for your check. Those are instance variables for your check, and Clang-tidy has a framework with which you can expose configuration these properties to the user, and the user can come in and interact and set those options for you and query those options, and your check can use them internally, the user-defined values. For example, here we have two properties, tolerance and target function, let's say, an integer and a string, because I wanted to have different types, and you can default initialize them. For example, zero value tolerance, I don't know what that means, but I made up some property. And the default target function is get underscore if the user doesn't specify any other target. But I'm going to let my user of this check specify its own target function by means of its prefix, because this is how I use it. I checked that pattern matches start with and the name of the prefix there. But I'm going to give the user control over this pattern and what to look for. And I'm just going to store these options, and the user can specify them from the command line or from Clang-tidy config files. Clang-tidy config files are configuration files that you can give Clang-tidy and automatically loads all those options. This is how you would specify config options in Clang-tidy configuration file. The default naming is .clang-tidy. And I've labeled them A1, B1, A2, B2 there, just for the sake of the slide, so it fits. So this is how the config would look like if you would pass it in command line format, but it's much more readable in Clang config format, of course. You can write unit tests for your checks. There's even a script that generates some sample files that get you started, but you have to write those yourself. Of course, the art of writing and the most difficult part of writing a Clang-tidy check is actually knowing and getting used to the AST matcher and how it works. And you have to get you started, you can use the Clang check tool that's built in LLVM, and you can dump the AST for your CPP and examine its structure and see, oh, I'm going to target this record declaration, or I'm going to target this method declaration. So you can basically just discover the structure of your source code and see what you need to match there. So when you're defining your register function. So because I consider this the most difficult part in actually trying to work with the matcher to make sure it gets the right thing. You can write fancy checks, like Olaf is present at this conference as a tweet. You can write Parmesan, catch cheesy comments, bipartisan, find code that uses two different containers in a complementary way, or artisan, code that took the writer very long time to do and can be replaced with the library function. So you can get very fancy with your checks and do very specific project-oriented checks. And some of them have reuse values, some of them may be throwaway, kind of onesie. But do write your own checks and run them regularly. And you can use recently in the newest Clang Power Tools version, you can specify your own Clang-tidy custom builder. And if you have a custom build of tidy, you can actually leverage that instead of the built-in LLVM one. So more sessions. I had more material around strings and dangling references. I would urge you to watch several presentations that have very good value on the lifetime profile and its implementation from the CPP core guidelines. It's a very nice session from CPP-Con last year. There are a series of very good articles on the MSDN, on the Visual C++ team blog by Stephen Kelly on extending Clang-tidy and using the AST matchers and Clang query and building your own Clang tooling. I think there are 5 or 6 articles on this topic, and I consider them the very best documentation right now on extending Clang-tidy and working with AST and Clang tooling on any platform. So I highly encourage you to read those articles. They're a bit lengthy, but they're very nice examples and a lot of information. So when you get the slides, you have all the links right there. Everything is linked there. Future developments for Clang-tidy and DST matchers, and a very recent session from Code Dive, just from the end of last year, again from Stephen Kelly, on refactoring your code base with Clang tooling. Again, a very nice session. I urge you to watch it. So with that, thank you very much. We don't have very much time.